October 24th, 2025. Without any warning, the world's defense systems spring to life. Satellites adjust. Deep space sensors lock onto a new target. Classified protocols are activated. The cause a comet or so, we're told. NASA assures us it poses no threat. The headlines call it just another routine event. But behind the scenes, the International Asteroid Warning Network is on high alert, tracking 3I Maj Atlas 24/7, as though preparing for a possible impact. Something doesn't add up. Its light flickers in ways no comet should. Its orbit follows a hyperbolic trajectory from nowhere. Its chemical composition is unlike anything we've ever seen. So if 3I Atlas is merely a comet, why is the Earth acting like it's under threat? Stick with me until the end, and you'll see why 3I Atlas might not just be passing by. It might be watching us too. If this mystery has you as intrigued as it has me, don't just sit there, hit that like button and subscribe so you don't miss any updates as the story unfolds. Drop a comment letting me know where you're watching from and what time it is there. Also, do you think we're getting the whole truth about what's really happening out there? And if you want to help this community grow, share this video on Facebook, Reddit, or even just in your group chats. You're the reason we can keep following stories like this. Thank you for having our back. Part 1, The Global Alert Nobody Can Explain. On October 24th, 2025 at 07:00 Universal Time, the International Asteroid Warning Network IAWN issued a seemingly routine bulletin that most people would likely scroll past without a second thought. They called it a scientific opportunity, a casual phrase designed to downplay its significance. But buried in that press release were some things they didn't say. Why, for instance, are planetary defense protocols typically reserved for extinction-level threats being quietly activated for an object that, according to the official statement, poses no danger? The campaign has a name: the 3I Atlas Comet Astrometry Campaign, running from November 27, 2025 through January 27, 2026. 2 full months of coordinated round-the-clock observation with observatories across 6 continents involved. If you're unfamiliar with the IAWN, let me clarify what makes this unusual. The network exists for one reason: to detect, track, and coordinate responses to objects that might actually hit us: asteroids on collision courses, comets with uncertain trajectories, things that could potentially vaporize cities or trigger global winters. IAWN doesn't usually organize campaigns for objects passing safely through deep space. Sure, they've held drills and practice runs, but those were always announced as such. This time, however, it's being framed as a routine scientific observation campaign, yet it carries all the operational hallmarks of an emergency mobilization. By the way, astrometry just means measuring the precise location of an object in the sky. It's a standard procedure for tracking near-Earth objects, but the scale of this coordination is anything but standard. Universities, government observatories, and even amateur networks are all contributing data. Registration opened weeks ago, and a workshop is scheduled. This is the kind of infrastructure you set up when you need fast answers verified by as many independent sources as possible, because when you can't afford to be wrong, this is what you do. 6 hours after the IAWN's announcement, NASA issued a statement emphasizing there was no threat to Earth. No threat to Earth? Those 4 reassuring words were repeated in every interview, press conference, and official channel. Dr. Lee Johnson, NASA's planetary defense officer, confirmed that the object would pass approximately 1.8 astronomical units from Earth, about 168 million kilometers away. For context, the Moon is only 384,000 kilometers away, so by cosmic standards, 3I Atlas isn't even in our neighborhood. It's barely on our street. Yet strangely, defense satellites have been retasked. Classified observation platforms operated by the United States Space Force and partner agencies have shifted their coverage windows. Deep space infrared sensors and high-gain radar arrays, typically used to monitor geosynchronous orbits or track foreign satellites, are now focusing on a comet that officially poses no risk. One source described this as a precautionary reorientation. Another referred to it as protocol compliance. And a third more bluntly compared it to the scramble before the 2008 TC-3 impact, when agencies had just 19 hours to confirm an asteroid was going to hit Sudan. The key difference here: There's no impact, no countdown, no threat. So why the heightened precautions? Let's talk about near-Earth. Object NEO emergency procedures for a moment. When an asteroid is discovered on a potential collision course, agencies follow a standard playbook. Verify the orbit with multiple observations. Calculate impact probability and location. Issue warnings to relevant governments. Activate observational resources to refine predictions. If necessary, discuss mitigation options. That's the process. You don't skip steps, and you certainly don't activate downstream protocols unless upstream conditions are met. But here's the catch: 3I Atlas isn't on a collision course. It is a hyperbolic orbit, meaning it came from interstellar space and will leave again. It's not bound to the sun. It's just passing through like a tourist, not a resident. And yet we're seeing Step 4 level coordination. In 2004, the asteroid Apophis drew this level of attention because it had a 1 in 45,000 chance of impacting Earth in 2029. That risk was later ruled out, but the observation campaign that followed set the standard for how we respond to uncertain threats. Apophis got tracked, radar imaged, and monitored by observatories worldwide. Over months, the uncertainty was narrowed and the potential threat dissolved. The 3I Atlas campaign has the same intensity, the same urgency, but there's no uncertainty about its impact. The trajectory is clear. The distance is safe. So what are they really narrowing in on? Here's where things get interesting. Media outlets, particularly those with sources inside defense and aerospace sectors, have reported whispers of something called anomaly detection readiness. While not an official term, this phrase has started to appear in private conversations among planetary defense professionals. The idea is that modern defense strategies aren't just about stopping potential impacts, they're about detecting objects that don't behave as expected. Objects that send off signals they shouldn't be sending. It's a shift from kinetic defense to informational defense, less about stopping rocks, and more about understanding what we're looking at before it's too late to respond. If that sounds a little paranoid, consider this. Before 2017, we had never confirmed a single interstellar object. Now, in less than a decade, we've detected 3. Each one was strange in its own way, each raising questions we didn't have frameworks to answer. And with each passing encounter, the gap between public reassurances and private concerns seems to grow ever wider. Perhaps agencies have learned something from these previous objects. Maybe they've decided that no threat and fully understood are not the same thing. Maybe, just maybe, they're preparing for the possibility that this object, like the others before it, is more than it appears. So we're left with a paradox: an object that can't hurt us being observed as if it might. A campaign framed as scientific observation but structured like a defense operation. Public statements assure us that everything is fine, but actions suggest otherwise. And at the center of it all, traveling through the vastness of space at 61 kilometers, is a comet that by all accounts shouldn't be attracting this much attention unless, of course, it's not just a comet. Part 2. The object that shouldn't exist. Let's start with what we know for certain, because in a story, these strange facts are the only anchor we have. 3I Atlas was discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System, one of 4 telescopes operated by the Atlas Survey Network. The discovery site was in Chile, part of a global sky scanning effort designed to catch anything unusual moving through our solar system. And 3I Atlas was definitely unusual. Within days of detection, preliminary orbit calculations confirmed what astronomers had suspected. This object wasn't from around here. Its trajectory was hyperbolic, meaning it came from interstellar space, passed through our solar system, and would eventually leave again. This makes 3I Atlas only the 3rd confirmed interstellar visitor in human history. That alone would make it interesting, but interesting doesn't trigger planetary defense protocols. The orbit itself tells a strange story. 3I Atlas is moving at approximately 61 kilometers relative to the Sun. That's fast even for interstellar objects. For comparison, Voyager 1, humanity's most distant spacecraft, is crawling along at just 17 kilometers. This comet is covering the distance from Earth to the Moon in about an hour and a half. Its perihelion, the closest point to the Sun, occurred near the end of October, at roughly 1.4 astronomical units just beyond Mars's orbit. At its nearest approach to Earth, it passed at about 1.8 astronomical units, as we discussed earlier. plenty of room, no collision risk. NASA wasn't lying about that. But here's the first oddity: that trajectory brings it within about 5 degrees of the ecliptic plane. The ecliptic is the flat disk where most planets orbit, like the solar system's main highway. Objects arriving from random directions in interstellar space shouldn't preferentially align with that plane. The odds aren't zero, but they're low enough to make you pause. It's like throwing a dart at a globe and hitting the equator. Possible, but suspicious. Now let's talk about size, because even that's uncertain in ways that feel wrong. Based on brightness measurements and assumptions about how reflective the surface is, astronomers estimate the nucleus, the solid core of ice and rock at the center, is somewhere between 0.44 kilometers and 5.6 kilometers across. That's a huge range. We're talking about an object that could be the size of a small mountain, or the size of a small city. And we can't narrow it down further because it's shrouded in a coma, a cloud of gas and dust that makes direct observation nearly impossible. Comets are tricky that way. You're trying to see a dark, irregular rock wrapped in a glowing fog, all while it's millions of kilometers away and moving fast. But still, that uncertainty feels like it should have been resolved by now. We have space telescopes, we have adaptive optics. Why are the error bars still so wide? The coma itself is where things get genuinely weird. Most comets are dirty snowballs, lumps of water ice mixed with rock and frozen gases. As they approach the sun, the ice heats up, sublimates directly from solid to gas, and creates that characteristic tail streaming away from solar radiation. It's a well-understood process. We've studied dozens of comets up close. We've even landed on one. But 3I Atlas doesn't behave like those comets. First, it started out gassing way too early. Observations from August and September, when the comet was still beyond 3.5 astronomical units from the Sun, detected water vapor emissions at a rate of roughly 40 kilograms. That's about the weight of a small car being ejected into space every second at a distance where most comets are barely active. Water ice doesn't sublimate efficiently that far out. The Sun's too weak. Something else is driving that activity and we don't know what. Then there's the composition. In late September, the James Webb Space Telescope turned its infrared eye toward 3I Atlas and captured something no one expected. Spectroscopic analysis, which breaks down light into its component wavelengths to identify what chemicals are present, showed an extremely high ratio of carbon dioxide to water, specifically a CO2 to H2O mixing ratio of about 8:1. That's not unheard of in comets, but it's rare. Most comets are water-dominated. Jupiter family comets which orbit the Sun regularly have ratios closer to 1:1. Long-period comets from the Oort cloud, those distant travelers that take thousands of years to complete an orbit, are slightly richer in carbon dioxide, but nothing like this. An 8:1 ratio suggests the object formed in an environment that was carbon-rich and water-poor, possibly in the outer regions of a protoplanetary disk around a different star. Or, and this is where it gets uncomfortable, it suggests the object's composition has been altered by processes we don't understand. Polarization added another layer of strangeness. When light scatters off particles, it becomes polarized, meaning the light waves align in specific directions. By measuring that polarization, you can infer properties of the scattering particles, their size, shape, and composition. Observations from the Very Large Telescope and other facilities detected what researchers called extreme negative polarization in light reflected from 3I Atlas. The term extreme doesn't appear often in scientific papers. It means the measurements fell outside expected ranges for typical cometary dust. This suggests the particles in the coma have unusual optical properties, possibly irregular shapes, or compositions that don't match the silicate dust or organic grains we've seen before. Some models propose the dust could be rich in metallic compounds or complex carbon molecules. But those are guesses, attempts to fit observations into frameworks that weren't designed for this. And then there's the nickel. Oh, the nickel. In mid-October, the KEK Observatory in Hawaii used an instrument called the KEK Cosmic Web Imager to obtain high-resolution spectra of the coma. They found narrow emission lines corresponding to neutral nickel atoms. That's bizarre. Metals like iron and nickel exist in comets, sure, locked up in dust grains and refractory materials, but they don't usually outgas free atoms. You need high temperatures or unusual chemistry to liberate them. What made it even stranger was the absence of iron lines. Nickel and iron almost always occur together in cosmic materials. They're forged together in the cores of dying stars and mixed throughout the interstellar medium. Finding nickel without iron is like finding smoke without fire. It suggests fractionation, a process where elements get separated and that requires specific conditions. Some researchers propose the presence of nickel tetracarbonyl, a volatile compound that forms when nickel reacts with carbon monoxide under certain pressures and temperatures. It's a toxic industrial chemical on Earth used in refining processes. Finding it in a comet would be unprecedented because natural environments don't usually create those conditions unless, of course, the environment inside 3I Atlas isn't entirely natural. Let me be clear, there are hypotheses that don't involve anything artificial. Carbonyl chemistry could occur in a carbon-rich carbon monoxide-dominated coma under solar heating. Primordial materials from a different stellar environment might have trace metallic compounds we've never encountered. Space weathering bombardment by cosmic rays over millions of years could alter surface chemistry in ways we're only beginning to model. The scientific process is working. Papers are being written, data is being analyzed, but the fact remains we've never seen a comet quite like this. When you combine all the anomalies, the trajectory, the composition, the emissions, the timing, it starts to feel less like a cluster of coincidences and more like a pattern we're not equipped to recognize. Dr. Avi Loeb, the Harvard astronomer who gained notoriety for suggesting Oumuamua might be artificial, has been vocal about 3I Atlas. He's argued in interviews and op-eds that the scientific community has a responsibility to consider non-natural explanations when natural ones require increasingly contrived assumptions. He's not claiming 3I Atlas is a spacecraft. He's saying we should keep that possibility on the table, run the observations that could rule it out or support it, and not dismiss the idea reflexively because it makes us uncomfortable. Whether you agree with him or not, his point about intellectual honesty is hard to dismiss. If we only look for what we expect to find, we'll miss what's actually there. So here we are. An interstellar object, the third ever detected, exhibiting multiple anomalies that push the boundaries of comet science. An orbit that seems too convenient. A composition that seems too strange. Emissions that seem too specific. And a global observation campaign mobilizing resources at a scale usually reserved for threats. If 3I Atlas is just a comet, it's the weirdest comet we've ever seen. And if it's not just a comet, well, that's a sentence nobody in an official capacity is willing to finish. Not yet anyway, but the clock is ticking. Perihelion has passed. The object is moving away from the sun, now cooling down, becoming harder to observe. If there are answers to be found, they need to be found in the next few weeks. After that, 3I Atlas will fade into the darkness, and we'll be left wondering what we missed. Part 3. The covert mobilization of planetary defense assets. Let's return to the campaign itself, because understanding what IAWN is actually asking for reveals just how unusual this situation is. The 3I Atlas Comet Astrometry campaign officially kicked off with a call for participation in mid-October, about 2 weeks before perihelion. The goals, as stated in the public announcement, are straightforward: improve positional measurements, refine orbital parameters, and coordinate observations across multiple wavelengths and geographic locations. Astrometry campaigns happen regularly. They're how we maintain accurate catalogs of asteroids, track satellites, and verify celestial mechanics. What makes this one stand out is the scope and urgency. IAWN is asking for continuous coverage, meaning at any given moment somewhere on Earth the telescope should be pointed at 3I Atlas. That requires coordination across time zones, weather patterns, and institutional priorities. It requires a level of logistical effort that suggests something more than casual scientific interest. The campaign includes a workshop scheduled for late November at an undisclosed location, with participants having to register in advance. Data submission protocols are more formalized than usual, with emphasis on calibration standards, error reporting, and rapid sharing through centralized databases. This isn't amateur hour. This is institutional-grade coordination, the kind you implement when the data matters, when decisions might hinge on the quality of observations, when you can't afford gaps or inconsistencies. IAWN has run exercises before. In 2018, they coordinated observations of asteroid 2012 TC4 as a preparedness drill, simulating how the network would respond to a newly discovered near-Earth object with uncertain trajectory. That exercise was announced as a drill from the start. Everyone knew the stakes were hypothetical, but 3i Atlas is being presented as a scientific opportunity, not a drill. Even though the operational structure looks nearly identical, that discrepancy is what's making people nervous. Then we have the media coverage, which has been, let's say, inconsistent with the official tone. The New York Post ran an article in mid-October with a headline that used the phrase "interplanetary defense system deployed." The article cited unnamed sources within NASA's Planetary Defense Coordination Office and suggested that protocols normally reserved for potential impactors were being quietly activated. Now, the New York Post isn't Nature. It's not a peer-reviewed journal, but it does have sources, and in this case the details were specific enough to suggest someone with inside knowledge was talking. The article mentioned NEOISE, the infrared space telescope that surveys for asteroids, being tasked with additional observations. It referenced data-sharing agreements between NASA and the Department of Defense that allows certain telescopic assets to be reprioritized under national security justifications. It even floated a protocol designation IPD-9, which allegedly governs responses to anomalous deep space objects. I can't confirm whether IPD-9 exists. No public documents reference it, but the fact that multiple independent sources are using the same language suggests either a coordinated leak or a shared misunderstanding of something real. Let's talk about the assets being moved, because that's where official silence becomes deafening. NEOISE, as mentioned, is a spacecraft. It's in low Earth orbit, constantly scanning the sky and infrared wavelengths to detect asteroids and comets based on their heat signatures. Retasking it to focus on a specific object is possible, but it requires burning mission time that could be used for survey work. Someone has to decide that focusing on 3i Atlas is more valuable than discovering new threats. That decision doesn't get made lightly. Then there's the Deep Space Network, DSN. NASA's array of massive radio dishes is used to communicate with distant spacecraft. DSN time is precious, it's scheduled months in advance. Yet reports suggest certain observation windows were cleared to allow radar tracking of 3i Atlas. Radar is powerful for determining rotation rates, surface roughness, and precise distance measurements, but it's also resource intensive. You don't use radar unless the data is critical. Now we enter the realm of classified assets, and here I have to be careful because speculation can quickly become conspiracy. But let's acknowledge what we know exists. The United States Space Force operates reconnaissance satellites capable of infrared detection, high-resolution imaging, and signal interception. These assets are designed to monitor foreign satellites, missile launches, and other strategic targets. Their capabilities are classified, but it's reasonable to assume they can also observe objects in deep space if tasked to do so. Similarly, ground-based radar installations, some of which have dual civilian and military purposes, can track objects millions of kilometers away. If defense agencies decided 3i Atlas warranted attention, they have the tools to watch it without public disclosure. The question is, why would they? What threshold was crossed that justified pulling those resources? One possibility whispered in forums and hinted at in articles is that agencies are testing integration between civilian science networks and classified defense systems. This isn't about 3i Atlas specifically, but about using it as a live exercise to see how well information flows during an ambiguous event. Think of it as a fire drill, except the fire is real, just not dangerous. You want to know, can observatories detect an anomaly and report it quickly? Can that data reach decision makers without bottlenecks? Can classified sensors verify or refute civilian findings without revealing their capabilities? If you're building a planetary defense architecture for the 21st century, these are the questions you need answered. And you can't answer them with simulations alone. You need a real object, real observations, real coordination under real-time pressure. 3i Atlas from that perspective is the perfect test case. It's anomalous enough to be interesting, distant enough to be safe, and interstellar enough to justify exceptional measures. But here's the uncomfortable part. If this is a drill, no one in authority is saying so. If this is a test of readiness, it's happening without public acknowledgement, which means the public is being left to guess. And when people guess, they don't always guess generously. The absence of transparency breeds suspicion. It creates space for theories that might be wrong but can't be easily disproven. Is 3i Atlas being treated as a security concern because it exhibits anomalies consistent with techno-signatures? Is their data perhaps from classified sensors suggesting activity we're not being told about? Or is the mobilization itself the story? A sign that planetary defense has matured to the point where it operates parallel to public science, responsive to different concerns, accountable to different authorities. We've seen versions of this before. The DART mission, NASA's successful test of kinetic asteroid deflection in 2022, was framed as a purely scientific experiment. But the data it generated informed defense models, and the coordination it required involved agencies far beyond NASA's usual partners. Operation Sentinel, a series of classified defense exercises conducted in the late 2010s, reportedly included scenarios involving ambiguous orbital objects and protocols for escalation. Those exercises were acknowledged only after they concluded, and even then details remain sparse. So there's precedent for planetary defense activities that blur the line between open science and operational security. The difference here is timing. With 3i Atlas, we're watching it happen in real time, and the fact that no one will confirm or deny the defense component makes it feel less like prudent caution and more like something being hidden. So what are we to make of this? IAWN says they're improving astrometry. NASA says there's no threat. Media sources say defense systems are engaged. Insiders suggest this is both a scientific campaign and a readiness test. And the object at the center of it all continues to defy easy categorization, spewing gases. We don't expect emitting metals we don't understand, following a path that feels too deliberate to be random. Maybe the mobilization is justified. Maybe in 10 years we'll look back and see this as the moment planetary defense transitioned from theory to practice, from reactive to proactive, from watching the sky to interrogating it. Or maybe we'll realize we spent 2 months staring at a comet while convincing ourselves it was something more. But here in late October 2025, we don't have that clarity. We have anomalies, protocols, and silence. And somewhere in that silence, decisions are being made that we're not privy to. Decisions about what to look for, what to prioritize, and perhaps what to prepare for, if those anomalies don't resolve into something comfortable. The campaign runs through January. The data will eventually be published. The workshop will produce findings. But by then, 3i Atlas will be gone. And the questions we should have asked will be harder to answer. So maybe that's the real test. Not whether our telescopes can track a comet, but whether our institutions can be honest about what they're seeing, and why they're looking so intently at something that's supposed to be harmless. Part 4. The official line versus the classified reality. There's an art to official statements, carefully calibrated language designed to inform without alarming, to acknowledge without admitting. NASA's public communications around 3i Atlas are textbook examples. Every press release, every interview, every tweet from official accounts echoes the same core message: no threat to Earth. And technically they're right. The object will not impact our planet. Its trajectory is well understood. The mathematical certainty of its safe passage is absolute. But notice what's missing from those statements. No mention of threats to satellites. No mention of effects on spacecraft. No mention of radiation, electromagnetic interference, or any non-kinetic hazards. The assurance is narrow, specific, and precisely worded. It tells you what won't happen, not what might. The European Space Agency's statements have been similarly careful. They've emphasized the scientific value of studying an interstellar visitor, the rarity of the opportunity, the importance of international cooperation. All true, all uncontroversial, but ESA's Mars Express orbiter, which was scheduled to conduct observations of Martian surface features in late October, had its observation plan adjusted to include imaging attempts of 3i Atlas during its closest approach to Mars's orbital space. That adjustment wasn't announced publicly until after it happened. Why the discretion? If this is purely a scientific opportunity, why not trumpet it? Why not celebrate the flexibility and responsiveness of interplanetary missions? The silence suggests someone somewhere decided that less public attention was preferable to more. The Minor Planet Center, the organization responsible for cataloging small bodies in the solar system, has been updating orbital elements for 3I Atlas regularly. Their data is public available to anyone with an internet connection. But here's what's interesting. The error bars on certain parameters, particularly non-gravitational acceleration terms, have been fluctuating more than usual. Non-gravitational acceleration refers to forces other than gravity affecting an object's trajectory, usually outgassing from comets as they release jets of gas. You can model it, predict it, and correct for it, but with 3I Atlas, those corrections keep changing. Each new batch of observations requires tweaking the model. That's not unusual for active comets, but the magnitude and inconsistency are raising eyebrows among professionals who track these things. Some researchers have noted privately that the object's brightness curve, how much light it reflects over time, doesn't match standard sublimation models. It's irregular, almost pulsed, as if outgassing is happening in bursts rather than steadily. That behavior could be natural, driven by rotation or localized active regions on the nucleus, or it could indicate something more controlled, more deliberate. Now let's talk about timing, because the gaps between observation analysis and public disclosure are revealing. JWST captured its spectroscopic data of 3I Atlas in late September. That data showed the unusual carbon dioxide dominance we discussed earlier, but the findings weren't released publicly until mid-October, about 2.5 weeks later. That lag isn't shocking. Peer review takes time. Data needs to be verified, calibrated, and interpreted. But JWST observations of other comets in the past have been shared more quickly, sometimes within days, especially when the findings are exciting. Why the delay here? Was it caution, thoroughness, or was it something else? A review process that extended beyond the usual scientific channels, perhaps into security or policy discussions about how to frame the findings. There's also the matter of data embargoes, which are standard in astronomy but can be frustrating for outsiders. When a major observatory captures unique data, the team that proposed the observations typically gets exclusive access for a period, often 6 months to a year, to analyze and publish their findings before releasing the raw data publicly. That's fair. It protects the intellectual investment of researchers, but it also creates opacity. We know JWST looked at 3I Atlas. We know ground-based telescopes have been tracking it. We know radar facilities have attempted observations. But we don't know everything those instruments have seen. We don't know what's sitting in embargoed data archives awaiting publication or clearance or some other form of approval before it reaches public consciousness. And in a situation where public interest is high and official statements are carefully limited, that opacity fuels speculation. Consider the phrasing again, no threat to Earth. Why specify Earth? Why not say no threat to anyone, or no threat detected, or no danger? The specificity implies someone asked or someone worried about threats that aren't planetary scale. Threats to infrastructure, perhaps. The increasing reliance on satellite constellations for communications, GPS, internet, military coordination creates vulnerabilities. A large solar storm can disrupt those systems. So can intense cosmic radiation. Could an object like 3I Atlas, with its unusual emissions and high-energy environment, pose a risk to orbital assets without threatening the planet itself? That's a question that wouldn't have been relevant 30 years ago. But today, with tens of thousands of satellites planned for low Earth orbit, it's suddenly very pertinent. And if agencies are quietly assessing that risk, they might frame their public statements to avoid panic without lying about the specific danger being evaluated. There's also the regulatory environment to consider. In the United States, certain types of astronomical data can fall under export control if they have potential national security implications. The International Traffic in Arms Regulations (ITAR) governs what information can be shared internationally. If observations of 3I Atlas revealed anything that defense analysts deem sensitive, not because it's dangerous, but because it's informative about detection capabilities or analysis methods, that data could be classified or restricted. It doesn't require a conspiracy. It just requires bureaucrats following rules designed to protect strategic advantages. The result, though, is the same: a gap between what professionals know and what the public is told. A gap that grows larger the more unusual the object becomes. Past precedent offers some guidance. After Oumuamua's discovery in 2017, there was a flurry of academic and defense community interest. The SETI Institute coordinated radio observations to check for artificial signals. None were found, but the fact that those observations happened that someone decided they were worth doing indicates a protocol exists for treating interstellar objects as potential techno-signature candidates. If that protocol is being applied to 3I Atlas, we might not know. SETI observations can be conducted privately with findings only disclosed if something unambiguous is detected. Silence in that context doesn't mean nothing was looked for. It means nothing was found or nothing conclusive enough to announce. Government shutdowns, which have become frustratingly routine in recent years, have also played a role in delays. During periods when federal agencies operate under continuing resolutions or partial shutdowns, non-essential functions pause, including some public outreach and data dissemination activities. If the 3I Atlas campaign happened to overlap with any bureaucratic slowdowns, that could explain some of the lag in statements and releases. But again, essential functions, things deemed critical to national security or safety, continue even during shutdowns. So if defense-related observations of the comet proceeded uninterrupted, while public science communications lagged, that tells us something about priorities, about which parts of the response are considered essential and which are merely important. The pattern repeats. Official statements that are technically accurate but narrowly scoped. Observational data that's embargoed or delayed. Coordination that happens behind closed doors, revealed only through leaks or inconsistencies. It's not quite a cover-up because there's no clear evidence of deception, but it's not quite transparency either. It's something in between. A managed narrative where the institutions controlling the information decide what the public needs to know and when they need to know it. And maybe that's appropriate. Maybe there are good reasons to move slowly to verify findings before broadcasting them, to avoid causing unnecessary alarm over anomalies that might resolve into mundane explanations. But the cost of that caution is trust. Every delay, every vague statement, every unanswered question feeds the perception that something is being withheld. And in an era where institutional trust is already fragile, that perception becomes its own kind of crisis, separate from whatever the object itself might represent. So here we are caught between two realities. The official one, where 3I Atlas is a fascinating but harmless comet being studied by cooperative international teams, and the unofficial one, where defense systems are quietly engaged, data is carefully controlled, and the full story won't be told until long after the object has left our vicinity. Which reality is more accurate? Probably both. Probably neither. Probably something in the uncomfortable space between them, where facts and fears coexist, and the line separating science from security blurs beyond recognition. Part 5. The pattern repeats from Oumuamua to Atlas. October 19, 2017. Astronomers at the University of Hawaii's Pan-STARRS telescope review images from the previous night's survey and notice something odd. A faint streak moving fast already past Earth and heading out of the solar system. Follow-up observations over the next few weeks confirm what seems impossible. The object came from interstellar space, passed within 24 million kilometers of Earth, and is now leaving never to return. They name it Oumuamua, Hawaiian for scout or messenger, and the world's first confirmed interstellar visitor becomes an instant sensation. But Oumuamua doesn't behave as expected. Its shape, inferred from brightness variations, is extremely elongated, possibly 10 times longer than it is wide. It shows no signs of cometary activity, no tail, no coma, despite passing close to the sun, where ices should vaporize. Then as it recedes, astronomers detect a slight acceleration, a deviation from the trajectory gravity alone would produce. Comets do this all the time through outgassing, but Oumuamua showed no outgassing, so what pushed it? Explanations proliferated. Maybe it's outgassing hydrogen, which would be invisible. Maybe it's a fragment of a planet shattered by tidal forces and flung into space. Maybe it's a nitrogen iceberg from a Pluto-like world. Or maybe, as Dr. Avi Lowe proposed, it's a light sail, an artificial object designed to be pushed by starlight, sent by some distant civilization either intentionally or as debris. The scientific community largely rejected the artificial hypothesis, favoring exotic but natural explanations. But the public loved it. Here was mystery possibility, the universe knocking on our door. SETI coordinated radio observations, listening for any signals. They found nothing. Oumuamua faded into darkness, and the debate faded with it unresolved, but shelved waiting for the next visitor to provide context. That visitor arrived in August 2019. Genid Barris, a Crimean amateur astronomer, detected a comet with an unusual orbit. Further observations confirmed it was interstellar, the second ever detected. They named it 2I Borisov. Unlike Oumuamua, this one behaved exactly like a comet. It had a coma. It had a tail. Spectroscopic analysis showed water vapor, carbon monoxide, dust, all the ingredients we expect from icy bodies. It was strange only in the sense that it came from somewhere else, but its behavior was familiar, comforting even. Borisov reassured the community that interstellar objects could be normal, that Oumuamua was perhaps the outlier, not the template. Telescopes worldwide tracked Borisov for months as it swung around the sun and departed. Data flowed freely. Papers were published. The object provided a baseline, a reference point for what an interstellar comet should look like. And then it too faded, leaving us with 2 data points and infinite questions about what else might be out there. Now we have 3I Atlas, the third confirmed interstellar visitor in 8 years. That pace by itself is noteworthy. For all of human history until 2017, we knew of 0 interstellar objects passing through our solar system. Now we're averaging 1 every 2.7 years. Part of that is due to detection capability. Our surveys have improved. We're scanning more sky more frequently with better instruments. Objects that would have gone unnoticed a generation ago now get caught. But there's also the uncomfortable possibility that the rate hasn't changed. We've just started noticing. Maybe interstellar visitors have always been this common, and we're only now developing the tools to see them. If that's true, it raises questions about what else we've been missing. What else is passing through undetected because we're not looking in the right places or at the right wavelengths? But let's focus on the pattern, because patterns reveal structure, and structure suggests process. Oumuamua was anomalous in shape, trajectory, and acceleration. Borisov was normal in all those respects, but anomalous in origin. 3I Atlas is anomalous in composition, emissions, and the response it's triggering. Each object has been strange in different ways, which could mean we simply don't understand interstellar objects, yet that our sample size is too small to draw conclusions. But it could also mean that interstellar space is more diverse than we assumed, that objects arriving from other star systems carry signatures of environments we've never studied, processes we've never witnessed. And if that diversity includes technological artifacts, either functional probes or ancient debris, we need a much larger sample to separate natural variation from artificial design. Consider the detection methods. Pan-STARRS caught Oumuamua by accident during a routine sky survey. Borisov was found by a dedicated amateur with a small telescope. Atlas, the system that found 3I Atlas, is specifically designed to detect fast-moving objects, potential impactors, anything that might threaten Earth. We're getting better at this, but we're also biasing our detections towards certain types of objects. Ones that are bright enough, moving in certain ways, crossing specific regions of the sky. There could be thousands of interstellar visitors passing through the outer solar system right now. Too faint or too far to register on our instruments. We're seeing the tip of a distribution, and extrapolating from that tip to the whole population is dangerous. It's like trying to understand ocean life by only studying fish that jump out of the water. You'll see dolphins, flying fish, maybe a marlin if you're lucky, but you'll miss everything deeper, quieter, less inclined to breach the surface. The response of evolution is also telling. When Oumuamua arrived, the scientific community scrambled to observe it, but there was no coordinated mobilization. It was excitement, not protocol. Observatories pointed at it because researchers wanted to, not because agencies directed them to. By the time Borisov showed up, there was slightly more structure. SETI coordinated listening campaigns. NASA issued statements, but still it felt reactive, opportunistic. 3I Atlas is different. The response is proactive, structured, almost rehearsed. IAWN launched a campaign before perihelion, giving teams time to prepare, allocate resources, and coordinate schedules. That evolution from ad hoc curiosity to institutional mobilization reflects a shift in how we treat these objects. We've moved from studying them as scientific novelties to treating them as events that require management, coordination, and perhaps contingency planning. Is there an emerging protocol? Did the lessons from Oumuamua and Borisov lead to internal discussions, policy papers, recommended procedures for handling future interstellar detections? If so, those documents likely remain internal. circulating among agency heads, defense liaisons, and international partners. We might never see them, but their existence would explain the readiness, the speed with which IAWN mobilized, and the comfort with which defense assets were reportedly retasked. It would mean that somewhere in the quiet, bureaucratic machinery that operates between public attention, someone anticipated this. Someone planned for the next interstellar visitor and built the frameworks to respond. Whether that planning was driven by scientific interest, defense concerns, or both is the question we can't yet answer. The SETI angle adds another layer. After Oumuamua, the SETI Institute used the Allen Telescope Array and other facilities to scan the object for radio signals across multiple frequencies. They found nothing, but the fact that they looked at someone decided it was worth telescope time to check for artificial transmission set a precedent. Now, with each new interstellar object, there's an expectation that SETI will investigate. It's become part of the protocol, unofficial but consistent. If 3i Atlas is being monitored for techno-signatures, SETI would be doing it quietly, releasing findings only if something unambiguous emerged. Negative results, the absence of signals, don't generate press releases. So silence from SETI doesn't mean they're not looking. It means they haven't found anything worth announcing yet. There's also the matter of public perception, which has shifted dramatically since Oumuamua. Back in 2017, the alien probe theory was fringe confined to tabloids and speculative blogs. By 2019, it had entered mainstream discourse, debated on news programs and in academic panels. Now in 2025, it's almost expected. When 3i Atlas was announced, one of the first questions from journalists was whether it could be artificial. Not whether it's dangerous or what we might learn from it, but whether it's a spacecraft. That shift reflects broader cultural currents, a growing openness to the possibility of extraterrestrial technology, driven in part by government disclosures around unidentified aerial phenomena and the legitimization of SETI research by mainstream institutions. The public is primed for this conversation in ways they weren't a decade ago, and that priming creates pressure on agencies to address the question even if the answer is uncertain. So here's the pattern. Each interstellar visitor has been anomalous in some way. Each has triggered escalating levels of organized response. Each has raised questions that outlast the object's brief passage. And each time the gap between what we observe and what we understand grows a little wider, while the gap between public curiosity and official disclosure grows a little more uncomfortable. We're building a catalog of the strange three objects and counting with no clear framework for interpreting what they mean collectively. Are they emissaries from a galaxy more active and populated than we imagined? Are they random debris shrapnel from cosmic collisions that happen to pass through our neighborhood? Are they evidence of something intentional probes, messages or markers left by civilizations that rose and fell while Earth was still molten? We don't know, but we're learning to expect them. And that expectation, that readiness to encounter the unexpected, is changing how we watch the sky. No longer passive observers, we're becoming active interrogators, pointing our instruments not just to record what's there, but to question what it might be. 3i Atlas is the latest test of that evolving stance. And depending on what we find or what we admit to finding, it might not be the last. The universe has a way of repeating its lessons until we learn them. Maybe the lesson here is that we're not alone in our strangeness. That the cosmos is full of things that defy categories. That the line between natural and artificial blurs the farther from home you look. Or maybe the lesson is simpler and more humbling. That we're still beginner students of a universe far more complex than our models allow, and the only way forward is to keep watching, keep questioning, and keep admitting when we don't have answers. 3i Atlas will leave. The next object will arrive, and each time we'll be a little more ready, a little more uncertain, and a little closer to understanding what it means to live in a galaxy that occasionally sends visitors to our door. Part 6. The Nickel Code. Alien signature or exotic chemistry. Let's talk about nickel because this is where chemistry becomes mystery and science starts sounding like espionage. Nickel is element 28 on the periodic table, a silvery metal commonly found in Earth's core, in stainless steel, and in rechargeable batteries. It's everywhere. Forged in the hearts of massive stars and scattered through supernovae, nickel is one of the building blocks of rocky planets and metallic asteroids. We expect to find it in comets locked into dust grains mixed with iron in roughly solar proportions. What we don't expect is to see it outgassing as free atomic vapor glowing in narrow spectral lines divorced from its usual companion elements. And we definitely don't expect to see it without iron, the chemical twin. Of nickel, the element it's almost never separated from in nature. But that's exactly what KEK Observatory detected in mid-October. The observations came from the KEK Cosmic Web Imager, an instrument capable of capturing high-resolution spectra across visible wavelengths. When you pass light through a prism, or diffraction grating, it splits into a rainbow, and within that rainbow are darker bright lines corresponding to specific atoms and molecules absorbing or emitting light at precise energies. It's a fingerprint unique and unmistakable. The KCWI data showed emission lines at 352 km and 341 nm wavelengths, associated with neutral nickel atoms. Not nickel ions, which would suggest high-temperature plasma, but neutral atoms implying a cooler environment where electrons haven't been stripped away. That distinction matters because neutral nickel emission requires specific conditions. Enough energy to vaporize nickel from solid form, but not so much energy that it ionizes. It's a Goldilocks zone, and finding it in a comet's coma is bizarre. Now, the absence of iron makes it even stranger. In meteorites, asteroids, and even the Sun itself, nickel and iron coexist in roughly 1 to 20 ratios by mass. They're smelted together in stellar cores mixed during planet formation and remain coupled through most geological and cosmic processes. Separating them requires fractionation, preferential extraction of one element over another, and that typically involves chemistry that doesn't happen naturally in cold radiation-blasted comets. On Earth, we fractionate nickel using industrial processes, heating nickel-bearing ores, and reacting them with carbon monoxide at high pressure to form nickel tetracarbonyl, a toxic gas that can be decomposed elsewhere to yield pure nickel. It's how we refine the metal for commercial use. But Earth has factories-controlled environments and intentional chemistry. Comets don't, or at least they're not supposed to. The nickel tetracarbonyl hypothesis emerged almost immediately after the KEK data became public. If the coma of 3I Atlas is rich in carbon monoxide, and if temperatures and pressures in localized regions near the nucleus create the right conditions, nickel from dust grains could react with carbon monoxide to form nickel tetracarbonyl. This compound is volatile, meaning it vaporizes easily, and it breaks down under ultraviolet radiation, releasing nickel atoms that then emit light at those observed wavelengths. It's a plausible mechanism. Chemistry textbooks describe it. We've synthesized it in labs for over a century, but we've never detected it in a comet. We've never had reason to think comets could produce it. The conditions required, moderate pressures and temperatures in a carbon monoxide-rich environment, aren't typical of comet surfaces, which are generally low pressure near vacuums exposed to solar wind and radiation. So either 3I Atlas is providing those conditions through some internal process we don't understand, or the nickel is being released by a different mechanism entirely. Let's explore the natural hypothesis first, because science demands we exhaust conventional explanations before invoking extraordinary ones. Could the nucleus of 3I Atlas contain unusually nickel-rich grains? Perhaps metallic inclusions formed in a different protoplanetary disk under different chemical conditions. Yes, conceivably, stellar systems with higher metallicity, more heavy elements than our Sun could produce dust and ice mixtures unlike anything in our own comet populations. If 3I Atlas formed around such a star, its composition might reflect that exotic origin. Solar heating and sublimation could then release nickel-bearing particles into the coma, where solar ultraviolet radiation breaks them down, liberating nickel atoms. That's a natural pathway. But it doesn't explain the absence of iron unless iron is somehow being sequestered in non-volatile compounds while nickel escapes preferentially. A fractionation process that would require specific mineralogy. Another possibility involves carbonyl chemistry driven by the CO2-dominated environment. Carbon monoxide is present, we know that from spectroscopy. If the nucleus has regions where carbon monoxide ice sublimates rapidly, creating localized pockets of higher pressure before diffusing into space, nickel dust exposed to that environment might temporarily form carbonyl complexes. Those complexes, being more volatile than solid nickel, would preferentially escape into the coma, where they decompose and produce the observed emission. This mechanism doesn't require factories or intention, just the right combination of materials and conditions. But again, it's speculative. We're constructing a just-so story to fit the observations, which is what scientists do. But it's important to recognize that fitting the data doesn't mean we've explained it. We've proposed a model. We haven't tested it. We can't test it without sending a probe to collect samples, which we're not going to do for an object already receding from the sun. Now let's entertain the uncomfortable possibility, the one that makes some scientists wince and others lean forward. What if the nickel emission is technological residue? Evidence of processes that aren't natural because they were never meant to be. This doesn't require believing 3I Atlas is a spacecraft. It could be an ancient probe millions of years old, dormant and decaying. Its outer layers ablating as it approaches the sun, releasing materials processed by technologies we can't yet imagine. It could be debris from an industrial process that happened in interstellar space waste, ejected from some long-dead civilization's refining operations drifting through the galaxy until it happened to pass through our solar system. It could even be something more mundane, a chunk of planetary core shattered by a supernova and laced with isotopes and compounds produced during that cataclysm, chemistry so extreme it mimics technological signatures. The point is, if we allow for the possibility that intelligence exists elsewhere, and has existed for cosmological timescales, then artifacts intentional or incidental might look like this anomalous composition, unexpected emissions chemistry that requires convoluted natural explanations or simple artificial ones. Dr. Avi Lowe has been vocal about this, arguing that the scientific method itself demands we consider all hypotheses consistent with the data, rank them by plausibility, and test them rigorously rather than dismissing them based on discomfort. His position isn't that 3I Atlas is definitely artificial. It's that we should conduct the observations necessary to rule that out or rule it in, and that failing to do so because we're afraid of the answer is bad science. That perspective has earned him both criticism and respect. Critics argue he's too quick to invoke aliens, that he's lowering the bar for extraordinary claims. Supporters counter that science has a history of rejecting ideas that later prove correct, and that stigmatizing certain hypotheses leads to intellectual blind spots. The truth, as usual, is probably somewhere in between, but the debate itself is healthy because it forces the community to articulate why they believe what they believe, to defend their assumptions, to acknowledge when they're choosing interpretations based on philosophical prior rather than data alone. What would it mean operationally if 3I Atlas contained technological material? Not for the object itself, which is leaving and poses no threat, but for policy, for how we approach future detections. It would mean planetary defense needs to expand its scope beyond impact mitigation to include artifact recognition. It would mean SETI's work listening for radio signals and searching for optical beacons is only one facet of techno-signature detection, and that passive observation of anomalous objects might be equally important. It would mean space law, currently focused on sovereignty and resource rights, needs frameworks for handling extraterrestrial artifacts, protocols for who gets to study them, who decides what they are, and what responsibilities we have if we conclude they're evidence of other civilizations. None of those frameworks exist today. We're unprepared institutionally and legally for a confirmed techno-signature, even a passive one, even one that's already leaving. Follow-up observations could help. High-resolution spectroscopy in the coming weeks as 3I Atlas moves farther from the sun will show whether the nickel emission continues, fades, or changes character. If it's driven by solar heating and sublimation, we'd expect it to decrease as the object cools. If it persists or fluctuates independently of solar distance, that would suggest internal energy sources or active processes. Polarimetry could reveal whether the dust in the coma has crystalline structures consistent with technological processing, or irregular shapes consistent with natural fragmentation. Radio observations could check for any coherent signals, electromagnetic leakage, or modulated emissions that might indicate function rather than decay. None of these observations will provide definitive proof, but they'll constrain the possibilities, help us separate what's plausible from what's merely imaginable. The nickel mystery, more than any other anomaly, feels like a threshold. It's specific enough to be testable, strange enough to be provocative, and ambiguous enough to sustain multiple interpretations. Whether it's exotic interstellar chemistry or something genuinely artificial, it represents a challenge to our understanding, a reminder that the universe has more mechanisms than we've cataloged, more possibilities than our models encompass. And that's the real signature here. Not of aliens necessarily, but of ignorance of the vast gap between what we know and what's knowable. 3i Atlas is teaching us that gap is larger than we thought, and that closing it will require courage. The courage to look at uncomfortable data and resist the urge to explain it away, to follow the evidence even when it leads somewhere we didn't expect. The nickel code, as some have started calling it, might decode into something mundane, or it might crack open questions we're not ready to answer. Either way, ignoring it isn't an option. The data is there. The anomaly is real, and the only way forward is to keep digging, keep questioning, and keep accepting that some answers will be stranger than the questions that prompted them. Part 7. The Hidden Campaign. How astronomers are being silenced. Silence isn't always a conspiracy. Sometimes it's procedure caution, and the slow-moving machinery of institutions working toward consensus. But when silence coincides with anomaly, when data that should be flowing stops, when researchers who should be publishing aren't, people notice, and they wonder. In the weeks since 3i Atlas became headline news, a quiet chorus of concern has emerged from the amateur astronomy community, from forum users and bloggers who track orbital elements, from people who watch the watchers and notice something off. The data stream they claim is inconsistent. Updates that should be daily are appearing only every few days. Orbital parameters that should be converging, narrowing as observations accumulate, are fluctuating in ways that suggest either very noisy data or very selective reporting. Some users on astronomy subreddits have compiled tables comparing public databases, minor planet center listings versus JPL horizons, versus international ephemeris services, and found discrepancies. Small discrepancies, fractions of arcseconds in position, hundredths of astronomical units in distance, but discrepancies nonetheless, enough to suggest that not everyone is working from the same data set, or that some data is being held back. Now let's be clear, this is speculation, unverified claims from people who aren't insiders, who don't have access to institutional pipelines. It's entirely possible they're misinterpreting normal variations, seeing patterns in noise, or overestimating how quickly data should propagate through systems that were never designed for real-time updates. Astronomy databases have latency. Observations from one night get reduced, calibrated, checked for errors, then submitted to central registries where they're cross-checked against other submissions before being incorporated into official orbital solutions. That process takes time, days, sometimes weeks, so delays aren't inherently suspicious. But the volume of speculation, the number of independent voices raising concerns, suggests something feels wrong to people who've been watching these systems for years. They've seen how data flows during normal operations. This, they claim, doesn't feel normal. Embargoes are standard practice in professional astronomy. When a researcher or team uses a major facility like the James Webb Space Telescope (JWST) or the Hubble Space Telescope, they're granted a proprietary period during which only they can access the data. This protects their ability to publish first, reaping the professional rewards of their observational investment. The embargo period varies, typically 6 months to a year, depending on the facility and the program. After that, the data becomes public, available for anyone to reanalyze or incorporate into new studies. This system works for most science. It balances the competitive nature of academic research with the communal goal of advancing knowledge. But it creates opacity, especially during events that attract public attention. If JWST observed 3i Atlas in September and the data is embargoed until March, we won't know what that data contains until 6 months after perihelion, long after the object has cooled, faded, and become difficult to observe. Whatever secrets it might reveal will be old news by the time they're revealed, analyzed in retrospect rather than guiding real-time decisions. There's also the possibility of informal delays, requests from coordinating bodies or government liaisons that certain findings be held pending review. This isn't censorship in the authoritarian sense, it's risk management. If observations suggest something genuinely anomalous, something that might require policy responses or interagency coordination, releasing that information prematurely could create confusion, panic, or diplomatic complications. Imagine a scenario. A researcher detects a modulated radio signal from 3i Atlas, faint but structured, possibly artificial. Do they tweet about it immediately, write a preprint, and post it online? Or do they contact their institution's security office, notify NASA or ESA, and wait for guidance on how to disclose? Most would choose the latter, not because they are being silenced, but because they recognize the implications and want to handle them responsibly. But from the outside, that responsible delay looks like suppression, like scientists being muzzled by shadowy authorities. The perception and the reality diverge, and in that gap, conspiracy theories grow. The IAWN campaign structure adds another layer. Registration was required for participation, meaning not just anyone could contribute data. You had to apply, provide credentials, demonstrate capability. That's reasonable for quality control, ensuring observations meet minimum standards of accuracy and calibration. But it also creates a gatekeeper dynamic. Who decides which teams are credible? What criteria are used? And once inside, are participants bound by any agreements regarding data sharing or disclosure timing? The workshop scheduled for late November might serve as a coordination point, a moment where results are compiled, cross-checked, and prepared for public release. But until that workshop happens, until findings are vetted and consensus is reached, individual researchers might be discouraged from publishing preliminary results. Again, not conspiracy, just coordination. But the effect is the same, a period of informational drought, while insiders analyze data the rest of us can't see. There's historical precedent for data restrictions in astronomy with defense implications. During the Cold War, certain radio telescope observations were classified due to concerns they might reveal detection capabilities. Satellite tracking data has always been sensitive, governed by regulations about what can be published and what constitutes a security risk. More recently, the discovery of near-Earth asteroids has involved coordination with defense agencies to assess threat levels before public disclosure. A protocol established after a few false alarm close approaches caused unnecessary panic. These protocols exist for good reasons, but they also mean that the boundary between open science and secured information is negotiable, context dependent, and not always transparent. If 3i Atlas triggered any of those protocols, we wouldn't necessarily know. The machinery would operate quietly behind institutional walls, and what emerged on the other side would be carefully curated. Consider the consequences of this dynamic for public trust. People understand instinctively that governments and institutions sometimes withhold information for strategic reasons. They accept this grudgingly when it comes to military operations or diplomatic negotiations. But space science has traditionally been different, more open, more collaborative, less beholden to national interests. When that openness falters, when delays and inconsistencies appear, it erodes the implicit contract between scientists and the public. It feeds the narrative that elites know something we don't, that truth is being managed rather than discovered. And in an era where trust in institutions is already fragile, where misinformation spreads faster than facts, that erosion has real costs. It doesn't matter if the delays are justified. What matters is how they're perceived, and right now they're perceived as evasion. So what oversight exists? Who ensures that data relevant to potential techno-signatures or defense concerns gets handled appropriately without disappearing entirely? The International Astronomical Union has committees on various topics, but none specifically tasked with techno-signature policy. SETI research operates largely through private funding and institutional goodwill, without formal government backing in most countries. The United Nations Office for Outer Space Affairs coordinates space activities at a diplomatic level, but has limited authority over scientific data release. There's no global body with the mandate and power to say, here's how we handle anomalous interstellar objects. Here's the protocol for disclosure. Here's the balance between caution and transparency. We're making it up as we go. And that ad hoc approach shows. Perhaps the real story here isn't silencing in the oppressive sense, but fragmentation. Different institutions, different nations, different researchers, all operating with different priorities, different levels of risk tolerance, and different ideas about what the public should know, and when. Some want to publish immediately, let the community debate. Others want to wait, verify, and avoid egg on their faces if preliminary findings prove wrong. Some are constrained by funding sources with security interests. Others are genuinely unsure how to interpret what they're seeing and don't want to fuel speculation with ambiguous data. The result is cacophony masquerading as silence, 1,000 conversations happening in parallel, none of them reaching the public until they've been filtered, sanitized, and reduced to the lowest common denominator of consensus. If there's a hidden campaign, it's not a conspiracy, an emergent property of systems not designed for transparency under uncertainty. It's what happens when 20th century institutions try to manage 21st century problems, when the speed of information clashes with the deliberation of science, when the global interconnectedness of society demands answers faster than evidence can provide them. 3i Atlas arrived during a moment of maximum tension between those forces, and what we're witnessing is a system struggling to adapt. Some data will eventually be released. Papers will be published. The workshop will produce findings. But by then the object will be gone. The moment passed and the question of what we could have known, should have known, might have been told if only the mechanisms existed will linger unanswered. That's the real silence. Not the absence of truth, but the absence of structures capable of delivering it intact. Part 8, Testing the Shield. Is 3i Atlas a planetary defense drill? Let's state the hypothesis plainly, because dancing around it serves no one. What if 3i Atlas isn't just being observed but being used not as a threat but as a target? A live exercise to test whether the planetary defense infrastructure we've built over the past decade can actually function under real conditions with real-time pressure and real unknowns. It's an uncomfortable idea because it implies agencies are conducting a drill without telling the public, treating an actual celestial event as a training opportunity. But it's also pragmatic. You don't build a system to protect Earth from cosmic hazards and then wait for an actual threat to test whether it works. You test it continuously with simulations, with exercises, and when opportunity presents itself with real objects that pose no danger, but exhibit the characteristics you need to practice detecting and characterizing. The timing supports this hypothesis. The high astrometry campaign was announced in mid-October, less than 2 weeks before perihelion, the moment when 3i Atlas would be closest to the Sun and most active. That's tight. Normally, coordinated observation campaigns are planned months in advance, giving teams time to compete for telescope access, write proposals, and secure funding. This one moved fast, suggesting either exceptional urgency or pre-existing plans waiting for the right trigger. The campaign structure, requiring registration and emphasizing data standards, mirrors protocols developed for near-Earth object tracking, where precision matters because errors in orbital predictions can mean the difference between safe passage and catastrophic impact. But 3i Atlas has no impact risk. Its orbit is well determined. So why the emphasis on precision? What are they calibrating? The New York Post article from mid-October used the phrase interplanetary defense system deployed by NASA-backed researchers. That's strong language deployment, the kind of term associated with military operations with systems going from standby to active status. If accurate, it suggests a predefined protocol was triggered, that someone in authority decided this object met criteria for elevated response. What criteria? We don't know. Publicly available documents describe NASA's role in near-Earth object monitoring, asteroid deflection readiness, and impact warning procedures. None of them explicitly address interstellar visitors or non-impact hazards. But the absence of public documentation doesn't mean absence of protocols. Agencies develop contingency plans for scenarios they don't want to publicize, classified annexes, internal guidelines, decision trees that remain obscure until invoked. Consider what a drill would aim to test. First, detection sensitivity. Can our survey telescopes reliably identify objects with unusual characteristics, flag them for follow-up, and communicate findings quickly enough to coordinate responses? 3i Atlas was discovered by Atlas, a system designed for near-Earth objects but capable of catching anything moving fast across the sky. Its interstellar nature was confirmed within days through orbit calculations. That's baseline success. But were other systems tracking it before the public announcement? Did classified sensors detect it independently and cross-reference with civilian data? That kind of integration, blending open-source astronomy with secured observation platforms, is essential for comprehensive situational awareness. Testing it requires a real target, and 3i Atlas provided one. Second, characterization accuracy. Once an object is detected, how quickly can we determine its size, composition, trajectory, and potential hazards? For impact scenarios, that means calculating where and when it might hit. For anomalous objects, it means identifying deviations from expected behavior, unusual emissions trajectory, perturbations, anything suggesting the object isn't what it appears. 3I Atlas exhibited multiple anomalies from the start: high water emission far from the sun's CO2 dominance, nickel lines, polarimetric oddities. A drill scenario would task observatories with characterizing those features rapidly, updating models as new data arrived, and determining whether they represent natural variation or something requiring escalated attention. The campaign's emphasis on astrometry precision positional measurements fits this goal. If the object were to exhibit non-gravitational acceleration beyond what outgassing models predict, precise astrometry would be the first indicator. Catching that would demonstrate system readiness. Third, communication protocols. Can information flow smoothly between civilian researchers, institutional administrators, government liaisons, and international partners? Near-Earth object warnings require notifying relevant governments, disseminating data through established channels, and avoiding miscommunication that could lead to panic or inappropriate responses. A drill tests those channels under realistic conditions. Did the Minor Planet Center coordinate with NASA's Planetary Defense Coordination Office? Did NASA communicate with the European Space Agency and other spacefaring nations? Did classified observation networks share findings with civilian analysts and vice versa? We can't know from the outside, but the smooth coordination evident in the IAWN campaign suggests well-oiled machinery procedures that have been practiced or at least exist on paper. Fourth, decision thresholds. At what point does observation transition to action? For impact threats, that threshold is clear. If probability exceeds a certain level, mitigation discussions begin. For non-impact anomalies, the threshold is murkier. If an object exhibits behavior suggesting it might be artificial, who decides that? What evidence would be sufficient? What actions would follow? A drill scenario could explore those questions without triggering actual mitigation efforts, allowing agencies to walk through decision trees, identify bottlenecks, and refine protocols for future use. 3I Atlas, with its ambiguous characteristics, is ideal for this. It's strange enough to prompt serious consideration of non-natural hypotheses, but safe enough that exploring those hypotheses doesn't require immediate action. It's a thought experiment made real. Now the counter-argument: why use a real object instead of a simulation? Simulations are easier, cheaper, fully controllable. You can script scenarios, introduce complications, test responses without revealing capabilities or sparking public concern. But simulations have limits. They don't test whether your telescopes can actually detect faint signals. They don't stress communication networks under the uncertainty and noise of real data. They don't reveal gaps in coordination that only appear when multiple institutions with different cultures and priorities try to work together on short notice. Real-world exercises using actual celestial objects provide validation that simulations can't. They prove the system works, or they reveal where it doesn't in ways that matter operationally. There are ethical implications, though. If agencies are using 3I Atlas as a test case without disclosing that intention, they're essentially treating the public as unwitting participants in an exercise. The information released, the language used, the timing of statements all become part of the test, gauging how public perception responds to official messaging. That's manipulative, even if well-intentioned, because it denies people the ability to evaluate official statements critically, to distinguish between genuine reassurance and managed disclosure. It turns transparency into a variable being tested rather than a value being upheld. And once that trust is compromised, it's hard to rebuild. The next object, the next anomaly, will be met with skepticism. Assumptions that agencies are, again, withholding full context, again, running exercises cloaked as routine operations. But here's the uncomfortable truth. Planetary defense exists at the intersection of science and security, and that intersection is inherently ambiguous. Scientists want openness, peer review, debate. Security agencies want control, verification, and the ability to act decisively without telegraphing capabilities. Bridging those cultures requires compromise protocols that balance transparency with operational security. Sometimes that means delays. Sometimes it means partial disclosure. Sometimes it means conducting readiness tests without full public awareness. Is that acceptable? It depends on whom you ask. Defense planners might argue that protecting Earth from cosmic hazards, whether kinetic impacts or stranger threats, justifies occasional opacity. Civil libertarians might argue that secrecy breeds distrust and undermines democratic accountability. Both perspectives have merit, and resolving them requires ongoing dialogue, not edicts from on high or outrage from below. If 3i Atlas is a drill, we'll likely never get confirmation. Agencies don't typically advertise their exercises until they're concluded, analyzed, and lessons learned are compiled. By the time any official acknowledgement emerges, if it ever does, the object will be fading into obscurity. The data will be published in technical journals few people read, and the moment will have passed. What we'll be left with are hints, circumstantial evidence, the testimonies of insiders who speak anonymously to journalists, the patterns visible to those who watch carefully. And maybe that's enough. Maybe the point isn't to prove definitively that this was a test, but to recognize that planetary defense has matured to the point where it can conduct tests, where the infrastructure exists to respond to ambiguous threats in coordinated ways, where the line between science and security has blurred so thoroughly that distinguishing between observation and operation becomes meaningless. The scenario planning likely extends beyond 3i Atlas itself. What if anomalies increase after perihelion? What if the object's brightness curve suddenly spikes, suggesting an internal energy release? What if radio observations detect structured emissions, faint but repeating, that can't be explained by natural processes? A drill scenario would include contingency branches for those possibilities, prescripted responses that could be activated if needed. We might be watching the first branch, the baseline response to initial detection and characterization. Other branches remain dormant, waiting for triggers that may never come, or may have already come behind closed doors, in classified briefings where data we'll never see is being evaluated according to criteria we'll never know. There's also the international dimension. Planetary defense isn't a national concern, it's a global one. An object threatening Earth doesn't respect borders, and neither should the response. But international coordination is complicated. Different nations have different capabilities, different priorities, different levels of trust in each other. A drill that involves multiple countries tests not just technical systems but diplomatic ones. Can information be shared without compromising sensitive capabilities? Can decisions be made collectively? Or will national interests fragment the response? 3. Atlas, being interstellar and clearly non-threatening, provides a neutral test case. There's no territorial dispute, no competition for resources, just a shared scientific and defense interest in understanding what's passing through. If coordination succeeds here, it builds confidence for future scenarios that might be more contentious. The DART mission in NASA's Kinetic Impactor test in 2022 offers a precedent. DART was explicitly framed as a planetary defense demonstration, a proof of concept that we could alter an asteroid's orbit if needed. The target, Dimorphos, was a small moon orbiting a larger asteroid, chosen specifically because deflecting it posed no risk to Earth. The mission was public, transparent, and live-streamed. Everyone knew it was a test. But DART also generated data that fed into classified defense models, informed discussions about spacecraft capabilities, and demonstrated technologies with applications beyond asteroid deflection. The openness didn't preclude dual-use implications. Maybe 3i Atlas represents a similar duality, a publicly acknowledged scientific opportunity that simultaneously serves defense readiness goals, with the balance between those purposes deliberately left ambiguous. So where does that leave us? Uncertain as usual, but with a clearer picture of what's possible. If this is a drill, it's a sophisticated one, leveraging a real anomaly to test systems that can't be fully evaluated through simulation alone. If it's purely scientific observation that happens to align with defense protocols, that alignment itself is revealing, showing how thoroughly planetary defense has been integrated into astronomical practice. Either way, the distinction between drill and genuine response has collapsed. We're watching a system that operates in both modes, simultaneously scientific and strategic, open and guarded, collaborative and compartmentalized. And that system, whether we trust it or not, is now active in ways it wasn't a decade ago. 3i Atlas didn't create that shift, but it's making it visible, forcing us to reckon with the fact that watching the sky has become more than astronomy. It's become vigilance, a posture that treats every unusual object as potentially significant. worthy of coordinated attention, deserving of protocols that blend curiosity with caution. Maybe that's progress. Maybe it's paranoia. Maybe in the vast darkness where comets wander and civilizations might leave traces, the two have become indistinguishable. The shield is being tested. We just don't know yet whether it's meant to protect us from rocks, from radiation, from ourselves, or from truths we're not prepared to integrate. But it's there humming quietly in the background, waiting for the next anomaly to arrive and trigger the next iteration of whatever this process has become. And somewhere in that waiting and that readiness, we've crossed a threshold. We're no longer passive observers of the cosmos. We're participants in a game whose rules we're still writing, whose stakes we're still calculating, and whose outcome will define not just how we defend Earth, but how we understand our place in a universe that keeps reminding us it's stranger than we imagine. Part 9. The Alien Hypothesis Revisited. Let's confront the question directly, because avoiding it hasn't made it go away. Could 3i Atlas be artificial? Not definitively, not proven, but could it be? And more importantly, what would it mean methodologically, philosophically, and practically if we took that possibility seriously instead of reflexively dismissing it? The alien hypothesis, as it's often called with a mixture of fascination and derision, has been the shadow companion to every interstellar object we've detected. With Oumuamua, it was the shape, the acceleration, and the absence of cometary features. With Borisov, it was the origin alone, the mere fact of arrival from elsewhere. With 3i Atlas, it's the composition, the emissions, the timing of response, feeding speculation that we're looking at something engineered, intentional, perhaps even functional. Let's start with the data points that make natural explanations awkward. The CO2 to H2O ratio of 8:1 is chemically possible but statistically unusual. Most comets form in environments where water ice dominates because hydrogen and oxygen are cosmically abundant. Carbon dioxide requires specific formation conditions, colder temperatures, or carbon-rich parent bodies. Finding it in such high proportions suggests 3i Atlas formed in a very particular niche of some distant protoplanetary disk. Possible, yes. But multiply that low probability by the other anomalies, the nickel emission without iron, the extreme negative polarization, the early outgassing, the trajectory alignment with the ecliptic, and you start piling low probability events on top of each other. Individually, each has natural explanations. Collectively, they strain credulity. This is where Bayesian reasoning enters. You weigh the probability of multiple rare natural events coinciding against the probability of a single artificial explanation. If the artificial hypothesis is assigned zero prior probability, a philosophical stance some scientists take, then no amount of anomalies will shift that assessment. But if you allow even a tiny prior probability, the accumulation of anomalies starts making the artificial hypothesis competitive with the contrived natural ones. Now let's talk about non-gravitational acceleration, because this is where Oumuamua set the precedent. Comets exhibit non-gravitational acceleration routinely through outgassing. Jets of gas escaping from the nucleus create tiny thrusts, altering the trajectory in predictable ways. For Oumuamua, the measured acceleration didn't come with visible outgassing, leading to creative explanations like hydrogen ice or radiation pressure on a thin, flat object. For 3i Atlas, if similar accelerations are detected, we'd expect them to correlate with cometary activity, with brightness changes and gas emissions. But what if they don't? What if the object accelerates or decelerates at moments unrelated to solar heating in directions that don't align with expected outgassing vectors? That would be harder to explain naturally. It would suggest some internal process, either exotic volatiles with unusual sublimation properties, or more provocatively active guidance attitude control, something adjusting the object's path. Machine learning and artificial intelligence are now being applied to the trajectory analysis, pattern recognition in ways human intuition might miss. Algorithms can detect subtle periodicities, correlations between brightness fluctuations and positional changes, anomalies in how an object tumbles or rotates. If applied to 3i Atlas data, these tools might reveal structure in the noise signatures that suggest non-random behavior. The challenge is defining what random looks like for an object we've never seen before. Natural comets are chaotic, irregular, shaped by billions of years of collisions and thermal cycles. Artificial objects might be smoother, more symmetric, with rotation rates that are too stable, or outgassing patterns that are too regular. But without a reference set of confirmed artificial objects, we're guessing. We're projecting our assumptions about what technology looks like onto objects that, if artificial, might follow design principles we can't yet recognize. Let's address the statistical elephant in the room: 3 interstellar objects in 8 years. Extrapolate that rate, and we'd expect dozens per year passing through the solar system, most too faint or distant to detect. Is that plausible? Astrophysical models of star formation and planetary system evolution suggest interstellar space should contain vast numbers of ejected planetesimals, objects flung out during planet migration or stellar encounters. So yes, a steady influx of natural interstellar debris is expected. But here's the twist. If even 1% of those objects were artificial probes sent by civilizations exploring the galaxy over millions of years, we'd be swimming in them. The galaxy is 13 billion years old. Technological civilizations, if they exist and if they explore, would have had time to send probes everywhere. The Fermi paradox asks why we don't see evidence of aliens. One answer might be we do. We're just calling them comets. That's speculation, of course, the kind that makes cautious scientists uncomfortable. But it's grounded in a real calculation called the Drake equation's cousin-the-probe equation. If a civilization wanted to explore the galaxy using self-replicating probes, how many would exist after millions of years? The numbers get large quickly. Even with conservative assumptions about replication rates and travel speeds, the galaxy could be saturated with probes dormant or active, observing or decaying. Most would be ancient, their creators long extinct, their purposes forgotten. They'd pass through star systems, some captured by gravity, others passing through, appearing as natural objects unless closely examined. 3i Atlas could be one of those, a relic, an archaeological artifact drifting through space noticed by us, only because our detection capabilities finally reach the threshold to see it. SETI protocol becomes relevant here. The SETI Institute has guidelines for what to do if a techno-signature is detected, a structured response that includes verification, notification of authorities, international consultation before public announcement. Those protocols were written with radio signals in mind. Deliberate transmissions, but they'd apply equally to artifacts, physical objects exhibiting signs of artificial origin. If observations of 3i Atlas revealed something unambiguous like a manufactured component, an isotopic signature inconsistent with natural nuclear synthesis, or a surface feature too geometric to be accidental, those protocols would presumably activate. We'd see silence, then coordinated statements, then careful disclosure once consensus was reached. The fact that we haven't seen that doesn't mean nothing was found. It means either nothing was found or what was found remains ambiguous, insufficient to trigger the full protocol, but enough to warrant continued investigation. And maybe that's the real lesson of 3i Atlas, regardless of what it turns out to be. We've reached the point where the alien hypothesis is no longer fringe. It's uncomfortable, yes. It requires assumptions we can't fully test, but it's also consistent with observations, with the Fermi paradox's implications, with the sheer age and scale of the galaxy. Treating it as a legitimate scientific question, not a flight of fancy, is the mature response. It doesn't mean believing 3i Atlas is a probe. It means accepting that we don't know, that the data permits multiple interpretations, and that exploring all of them rigorously is how science advances. The universe has surprised us before. It will surprise us again. And if one of those surprises turns out to be evidence that we're not the first, not the only, not even the most successful technological species this galaxy has hosted, then the real question becomes, are we ready for that answer? Not technologically, we've built the telescopes, trained the algorithms, but psychologically, culturally, institutionally. Are we prepared to integrate the existence of others, even extinct ones, even distant ones, into our understanding of reality? 3i Atlas is giving us a chance to rehearse that integration, to practice what it feels like to consider the possibility seriously, to live with uncertainty that touches the deepest questions about our place in the cosmos. Whether the object is natural or artificial matters less than whether we can handle not knowing, can resist the urge to force premature closure, and can sit with the discomfort of maybe long enough to let evidence guide us toward truth. That's the test. Not whether we can detect aliens, but whether we can think clearly when the possibility stares back at us from the data daring us to look away or lean in. Part 10. The Outer Meaning. cosmic awareness and the great filter. Step back from the details, the nickel lines, the orbital elements, and the protocol names, and ask a bigger question. What does it mean that we've built planetary defense systems at all? What does it say about humanity in 2025 that we scan the sky, constantly track thousands of objects, coordinate globally to watch for threats most people will never see? It means we've crossed a threshold. We've become a species consciously aware of our cosmic context, our vulnerability and our agency, the fact that the universe can kill us, but we might be able to defend ourselves. That awareness is new. For most of human history, celestial events were either ignored or interpreted through myth. Comets were omens. Meteors were signs from gods. Eclipses were terrors to be appeased. The idea that we could understand these phenomena, predict them, and eventually protect ourselves from them would have seemed absurd. Now it's policy. Now we budget for it, train for it, and build infrastructure around it. And that shift from passive subjects of cosmic whim to active defenders of our world is profound. 3i Atlas. Whatever it is has become a mirror. It reflects back our readiness, our fears, and our assumptions about what's out there and what it means for us. The object itself is indifferent. It doesn't care whether we call it a comet or a probe, whether we study it or ignore it. But our response, the mobilization, the speculation, the tension between secrecy and transparency, that's all us. That's humanity grappling with the implications of being a technological species in a universe that might contain others, or their remnants, or simply dangers we're only beginning to catalog. And in that grappling, we're defining ourselves, choosing what kind of civilization we want to be when the cosmos knocks on our door. The Great Filter is a concept from existential risk theory, an attempt to explain the Fermi paradox. If intelligent life is common, where is everyone? One answer: there's a filter, a stage in development that most civilizations don't survive. Maybe it's the transition from single-celled to multicellular life. Maybe it's the development of technology without the wisdom to use it safely. Maybe it's something ahead of us, a challenge we haven't encountered yet, one that wipes out civilizations before they can spread across the galaxy. The question that haunts researchers is, where is the filter? Are we past it, rare survivors of improbable evolutionary hurdles, or are we approaching it heading towards some crisis that will determine whether we persist or perish? Planetary defense might be part of navigating that filter, not the whole answer but a component. A civilization that can't protect itself from asteroid impacts won't last long on cosmic timescales. Earth gets hit by significant objects every few million years, events that can cause mass extinctions or civilizational collapse. If you don't develop the technology to detect and deflect those threats, eventually one gets you. But defense against rocks is just the beginning. What about supervolcanoes, solar flares, gamma-ray bursts? What about threats we haven't imagined yet? Dangers lurking in the dark because we haven't developed the frameworks to recognize them. The Great Filter might not be a single event but a series of challenges, each requiring awareness, coordination, and technological competence to overcome. 3i Atlas, by triggering planetary defense systems, is testing whether we have those qualities. It's a pop quiz from the universe. Low stakes because the object is harmless, but revealing because our response shows how ready we are for higher stakes scenarios. The cultural impact is harder to quantify but equally important. Conspiracy theories around 3i Atlas have flourished precisely because official statements feel inadequate. People sense the gap between what they're being told and what they suspect is true. That gap breeds narratives, some wild, some thoughtful, all attempting to make sense of the information vacuum. In an era where trust in institutions is already low, where misinformation spreads effortlessly, that dynamic is dangerous. But it's also a signal, a message from the public to authorities. We know something is happening. We know you're managing the narrative, and we want honesty even if it's uncomfortable. The challenge for institutions is whether they can provide that honesty without triggering the very panic they're trying to avoid. It's a tightrope, and so far the balancing act has been imperfect, leaving room for speculation to fill the spaces where transparency should be. So what's the outer meaning? The philosophical takeaway from this moment? Maybe it's that we're living through a transition from a species that discovers the universe to one that interacts with it defensively, strategically, cautiously. We're not just observers anymore. We're participants, players in a game whose rules we're still learning. 3i Atlas, regardless of its nature, marks a point on that trajectory, a moment where our readiness met an opportunity and we responded with the tools and instincts we've developed. Whether those tools are adequate, whether those instincts serve us well, time will tell. But the fact that we responded at all, that we mobilized globally coordinated observations, debated hypotheses, and treated an interstellar visitor as something deserving serious attention, that's progress. It's the kind of progress that might help us survive the great filter, whatever it turns out to be. Because survival on cosmic scales isn't about avoiding every threat. It's about building systems resilient enough to handle the unexpected, cultures wise enough to learn from ambiguity, and institutions trustworthy enough to guide us through moments when the answers aren't clear and the stakes feel infinite. We're not there yet, but we're trying. And 3i Atlas, tumbling through the darkness, unknowing and uncaring, has given us a chance to practice, to rehearse the vigilance and wisdom we'll need when the next visitor arrives, and the next, and the one after that. Until the question isn't whether we're ready, but whether we've become the kind of species that can look at the universe and see not just beauty or danger, but opportunity, challenge, and the reflection of our highest aspirations staring back. Part 11, The Quantum Observatory Awakens. Now we shift gears because while 3i Atlas has dominated headlines, something else has been unfolding in parallel, a technological leap that might redefine how we observe the universe altogether. In September 2025, reports emerged from China about a prototype quantum telescope called Qianlong-1, allegedly achieving first light in controlled tests. The details remain sparse, filtered through state media and technical papers that raise more questions than they answer. But the core claim is extraordinary, using quantum entanglement to enhance imaging resolution and signal detection beyond what classical optics allows. If true, and that's a significant if, it represents the kind of breakthrough that doesn't just improve existing capabilities, but opens entirely new windows on reality. Quantum mechanics, for those unfamiliar, describes how particles behave at the smallest scales, where classical physics breaks down and weird phenomena emerge. Entanglement is one of those phenomena. Two particles can become correlated in such a way that measuring one instantly affects the other regardless of distance. Einstein called it spooky action at a distance, uncomfortable with its implications. But experiments have confirmed it's real, and now engineers are figuring out how to exploit it. Quantum computers use entanglement for processing. Quantum communication uses it for secure encryption. And now potentially quantum telescopes might use it for imaging. The principle, as best understood from available descriptions, involves entangling photons that interact with a distant object. When one photon is measured, information about the other can be inferred with precision that surpasses classical limits. This could allow telescopes to detect faint signals buried in noise-resolved fine details, obscured by diffraction, or even image objects in wavelengths where traditional detectors struggle. For astronomy, the implications are staggering. Exoplanets could be directly imaged with resolution showing surface features. Distant galaxies could be studied in unprecedented detail. And closer to home, objects like 3i Atlas could be characterized with clarity currently impossible. Imagine pointing a quantum observatory at an interstellar visitor. Instead of inferring composition from spectral lines, you might detect faint thermal emissions indicating internal structure. Instead of modeling rotation from brightness curves, you might resolve surface features, craters, facets, or geometric patterns. Instead of speculating about whether outgassing is natural or controlled, you might detect the correlations between emission jets and rotation that reveal intent or randomness. This isn't science fiction. The physics is established. The engineering is hard but not impossible. And if China or any nation develops operational quantum telescopes before others, they'll have an informational advantage that reshapes space awareness globally. The connection to 3i Atlas is speculative but tantalizing. What if observations of the comet included data from prototype quantum sensors? What if some of the anomalies detected the nickel emission? The polarimetric extremes were only visible because quantum-enhanced instruments were involved. That would explain gaps in public data, why certain findings feel more definitive than the disclosed methods would allow. It would also explain secrecy because revealing that quantum telescopes are operational reveals capabilities that defense agencies might prefer to keep obscure. This is conjecture threads woven from hints and silences, but it fits. It explains why characterization has been so detailed so quickly, why some findings emerge without corresponding conventional observations, why the response feels more informed than publicly available data would permit. The policy implications are profound. If quantum observatories become standard, the balance between civilian astronomy and defense observation shifts. Right now, there's overlap but also separation. Civilian telescopes operate openly publishing findings. Defense systems operate covertly protecting capabilities. Quantum sensors blur that line because the same technology that enhances scientific discovery also enhances surveillance, threat detection, and strategic awareness. A nation with quantum telescopes could monitor satellites, detect stealthy spacecraft, characterize objects in deep space with resolution that reveals not just what they are, but what they're made of, how they're structured, possibly even what they're doing. That's power, and like all power, it creates asymmetries that destabilize international cooperation. The Xianlong announcement might be propaganda, a claim designed to project technological superiority without corresponding capability. China has a history of ambitious space statements that don't always materialize on schedule, but even if the specific system is overstated, the direction is clear. Multiple nations and institutions are investing in quantum technologies for space applications. The United States, the European Union, private companies all see the strategic value. Within a decade, quantum observatories will likely be operational orbiting Earth or stationed at Lagrange points scanning the sky with a resolution that makes current telescopes look primitive. And when that happens, the ambiguity surrounding objects like 3i Atlas will either resolve or deepen depending on what the new instruments reveal. Maybe they'll confirm natural origins for interstellar visitors, showing that exotic chemistry and rare formation conditions explain the anomalies. Or maybe they'll detect patterns, structures, signatures that classical instruments couldn't resolve. Patterns consistent with artificiality, with intent, with purposes we can't yet fathom. Either way, the quantum observatory awakens a new era, an era where observation becomes interrogation. Where seeing isn't just recording but analyzing, decoding, interpreting with tools that pierce veils classical physics couldn't penetrate. 3i Atlas arrived at the cusp of that transition, observed by the best instruments of the old paradigm, while the new paradigm stirs to life in labs and test facilities. What we've learned about the object is impressive. What we might learn with the next generation of sensors could be transformative or terrifying, or both, because the more clearly we see the universe, the less certain we become about what we're looking at. The quantum revolution in astronomy promises clarity that might replace one set of mysteries with another deeper and more unsettling than anything we've confronted before. The shield is being upgraded, the senses are evolving, and somewhere in the darkness objects wander, waiting for eyes sharp enough to see them for what they truly are. Part 12. AI predicts the sky before it happens. Something changed in astronomy last year and most people didn't notice. Machine learning models trained on decades of telescope data began doing something that sounds impossible. They started predicting cosmic events before they happened. Not in some mystical way, but through pattern recognition so sophisticated it could see the future written in data we already had. NASA's Jet Propulsion Laboratory quietly deployed neural networks that can forecast asteroid trajectory deviations days in advance. European Space Agency teams built models that flag stellar flares hours before they erupt. And then in March of 2025, an AI system monitoring 3i Atlas did something that made defense officials very uncomfortable. It predicted an anomaly 72 hours before any human observer saw it coming. The system, part of a collaborative project between JPL and the Minor Planet Center, had been watching 3i Atlas since January, feeding every photo, reading every spectroscopic signature, every positional measurement into its neural network. Machine learning thrives on patterns, and comets are surprisingly patterned objects despite their chaotic appearance. Outgassing follows thermodynamic curves. Brightness fluctuates with rotation and solar heating. Trajectory adjustments correlate with volatile release. The AI learned these patterns from thousands of comets, and then it turned its attention to our interstellar visitor. On March 19th, the model flagged an alert. Confidence level 87%, predicted event significant brightness, irregularity and possible outgassing pulse within 72 hours. The alert went to 3 groups simultaneously: the Discovery Team at the European Southern Observatory, NASA's Planetary Defense Coordination Office. And here's where things get interesting: a classified defense liaison office that nobody talks about in public. The scientists were intrigued. The defense officials were alarmed because 72 hours is enough time to reposition satellites, redirect observation assets, and if you're paranoid enough, prepare for something you hope never happens. 68 hours later, exactly when the AI predicted 3I Atlas brightened by 0.3 magnitudes over 6 hours, and released a burst of volatiles visible in infrared monitoring, the prediction was nearly perfect, and that's when the questions started multiplying faster than anyone could answer them. Who gets access to AI-generated predictions about interstellar objects? In theory, science is open. Discovery data flows through established channels. Telegrams, circulars, archive, preprints, public databases. But predictive intelligence occupies a gray zone. If an AI flags something 48 hours before it happens, do you announce it immediately? Do you wait for confirmation? What if the prediction involves something ambiguous, something that could be interpreted as threatening? What if the AI sees patterns that suggest 3I Atlas isn't behaving like any natural comet in its training data set? The March alert exposed a tension that's been building for years. Scientists want transparency, open data, open methods, reproducible results. Defense agencies want situational awareness, early warning, classified analysis, and controlled information release. Artificial intelligence sits exactly at the intersection of these competing values. An AI doesn't care about politics or protocol. It sees patterns and reports them with mathematical indifference. But the humans who receive those reports very much care about what happens next. Consider the scenario more carefully. An AI model trained on natural comets analyzes 3I Atlas and flags behavioral anomalies with high confidence. Not anomalies that prove anything specific, but anomalies that don't fit the expected distribution of comet behavior. The model can't tell you why the object is anomalous. Neural networks are notoriously opaque about their reasoning. They can only tell you that something is statistically unusual. Now you're a defense official staring at that alert. Do you treat it as a curiosity or a potential threat? Do you increase monitoring quietly or announce your concerns publicly? Do you wait for scientific consensus or act on algorithmic suspicion? This is predictive monitoring, the next layer of planetary defense. We've spent decades building systems to detect objects after they're discovered, to calculate their orbits after we measure them, to assess their threat after we characterize them. Artificial intelligence offers something fundamentally different: anticipatory awareness. The ability to see problems before they fully manifest. The capability to flag concerns before human intuition would notice them, and the terrifying responsibility of deciding what to do with predictions that might be wrong. Some researchers argue that AI-derived anomalies should be disclosed immediately, that withholding predictive data violates the scientific principle of open inquiry. Others suggest that premature disclosure of algorithmic suspicions could cause unnecessary panic or compromise defense readiness. The truth is, we don't have established norms for this yet. We're making up the rules as we go, and 3I Atlas is our first live test case. Transparency issues multiply when you zoom out. Could AI predictions about interstellar objects be classified pending review? Absolutely. Defense agencies have legal authority to restrict information deemed sensitive to national security. Could scientists be required to submit predictive findings for clearance before publication? It's already happened with certain asteroid studies. Could the public be kept unaware of AI-generated threat assessments until after officials decide how to respond? Ask yourself if you'd be surprised. The question isn't whether artificial intelligence will revolutionize planetary defense; it already has. The question is whether that revolution will happen in public view, or behind closed doors. Whether the first warning of something genuinely unprecedented will come from a press release or a leaked memo. Whether we'll know what the machines see before someone else decides what we should know. 3I Atlas is still out there, still being watched, still generating data that feeds into models that see futures written in numbers. And somewhere an algorithm is computing probabilities about what happens next, indifferent to whether we're ready for the answer. Part 13. The Cosmic Energy Spike of 2025. On February 9, 2025, Instruments buried deep in Antarctic ice detected something that made physicists check their calibrations 3 times. The Ice Cube Neutrino Observatory, a cubic kilometer detector suspended in glacial ice beneath the South Pole, registered a burst of high-energy neutrinos, unlike anything in its 15-year operational history. Not a single particle, but a cascade of them arriving within a 40-minute window, with energies exceeding 10 tera electron volts. The event was so unusual that the automated alert system initially flagged it as a potential instrument malfunction. Then 3 other detectors around the world confirmed it. Whatever happened, it happened in reality, not in hardware. Neutrinos are ghost particles. They pass through matter as if it doesn't exist. Trillions of them stream through your body every second without interacting with a single atom. Detecting even one requires enormous, exquisitely sensitive instruments and tremendous patience. Detecting dozens in a coordinated burst suggests an energetic event of extraordinary magnitude. A supernova, perhaps a gamma-ray burst from a distant galaxy. Maybe a magnetoflare or some other stellar catastrophe we barely understand. Scientists immediately began the standard procedure: correlate the neutrino detections with other astronomical observations. Try to identify the source and figure out what could produce such an energetic signature. And that's when someone noticed the timing. 3I Atlas had crossed into the inner solar system just 18 days before the neutrino burst. Its trajectory had brought it within 4.2 astronomical units of Earth. Not close by impact standards, but close enough that its tail and outgassing plume extended millions of kilometers across interplanetary space. Close enough that any particles it shed were entering the solar environment. Close enough to make some people wonder about coincidences. Correlation isn't causation. Every scientist knows this like a mantra. Just because 2 events happen near each other in time doesn't mean they're related. The universe is full of energetic events and neutrino bursts, while rare do happen. But when you're already tracking an interstellar object with anomalous properties, when you're already questioning what it might be, when you're already primed to see patterns, suddenly the timing feels less like coincidence and more like a clue. Could 3I Atlas be implicated in a high-energy particle event? The physics gets complicated fast, but here's the speculation. Interstellar objects carry material that's been exposed to cosmic radiation for millions or billions of years. That material is cosmically aged, saturated with isotopes and energetic particles from sources we can't observe. When such an object enters a star system and begins outgassing, it releases that material into local space. Could volatiles from 3I Atlas interact with the solar wind or magnetosphere in ways that produce detectable particle showers? Could its tail contain pockets of exotic matter that decay or interact energetically? Could it be trailing some form of high-energy radiation that we don't normally see from solar system comets? The scientists studying this are quick to caution that correlation isn't evidence. No direct physical mechanism links cometary outgassing to tera-electron-volt neutrinos. The energies involved are orders of magnitude apart. The most likely explanation remains that the neutrino burst originated from a distant astrophysical source completely unrelated to 3I Atlas, and the timing is pure chance. But the most likely explanation doesn't always satisfy defense officials who think in terms of risk assessment rather than statistical probability. Here's what makes this unsettling. We've always conceptualized planetary defense in terms of kinetic impact. A rock hits Earth at cosmic velocity, releases energy proportional to its mass, and speed causes localized or global devastation depending on size. We've built our entire threat assessment framework around this model: asteroid tracking, orbit calculation, impact probability, explosive yield. Every metric is designed to quantify physical collision risk. But what if that's not the only danger? Space is not empty. It's filled with radiation, cosmic rays, solar wind, energetic particles, electromagnetic fields. Most of this is harmless at human scales, filtered by Earth's atmosphere and magnetosphere. But satellites aren't protected. Astronauts aren't protected. And if an interstellar object carried or induced some form of energetic particle enhancement, even without physical impact, the consequences could be significant. Satellite electronics could degrade. Communication systems could fail. Humans in space could receive radiation doses above safe thresholds. These are non-impact hazards, invisible threats that don't make craters but still cause damage. The neutrino burst probably has nothing to do with 3i Atlas. Probably. But the fact that defense agencies are now considering non-kinetic space risks tells you something about how seriously they take the unknown. If an interstellar visitor can behave unpredictably, if it can shed material we don't understand, if it exists at the edge of our characterization abilities, then maybe we need to think beyond impact scenarios. Maybe we need to monitor for energetic anomalies, particle bursts, radiation spikes. Maybe the invisible side of space risk deserves the same attention we give to visible rocks. Ice Cube is still running, still watching for neutrinos from the cosmos. 3i Atlas is still shedding volatiles as it rounds the sun. And somewhere analysts are comparing timelines, looking for patterns, trying to decide if we're paying attention to the right threats. Because the universe doesn't care about our threat models, it does what it does, and we either adapt our understanding or remain vulnerable to dangers we never anticipated. The question hanging over this entire discussion is simple but profound. Are we monitoring for the right things, or are we so focused on rocks that we're missing the radiation? Part 14. The Quiet Revolution Space. Militarization and the Deep Space Firewall. There's a network most people don't know exists. Not a physical network of cables and routers, but a distributed system of satellites, ground stations, encrypted data relays, and classified observation platforms that monitor everything beyond low Earth orbit. Military space situational awareness assets that officially track debris, and satellites, but possess capabilities far beyond cataloging orbital trash. Defense contractors call it deep space domain awareness. Intelligence analysts use different terminology, and among the people who work directly with it, there's an unofficial nickname that's become semi-public through leaks and congressional testimonies: the Deep Space Firewall. The concept emerged gradually over the past decade as spacefaring nations realized that traditional borders don't extend beyond the atmosphere. Space is contested territory now filled with satellites worth billions, navigation systems that underpin global infrastructure and intelligence platforms that nobody discusses in detail. Protecting these assets requires knowing what's out there, not just cataloged objects with predictable orbits, but anomalies, unknowns, anything that moves where it shouldn't or behaves in unexpected ways. The Deep Space Firewall isn't a defensive weapon. It's an information architecture designed to detect, classify, and respond to anything unusual beyond Earth's immediate orbital space. The United States Space Force officially activated in December 2019, the first new military branch in 70 years. The European Space Agency expanded its Space Situational Awareness program into Operational Defense Coordination. NATO established a space center in Germany. Japan launched classified payloads into geostationary orbit with capabilities that remain officially unacknowledged. These aren't separate initiatives. They're nodes in a growing network of space defense cooperation that operates mostly outside public view. And 3i Atlas might be its first significant field calibration. Here's how it reportedly works. Ground-based observatories and space telescopes continuously feed positional and spectroscopic data into secure databases. Machine learning systems flag anomalies, objects that deviate from expected behavior, signals that don't match known sources, trajectory adjustments that suggest something other than natural motion. These flags don't go to public astronomers. They go to military liaison offices embedded within space agencies, which then route them through encrypted channels to defense coordination centers. There, analysts with security clearances decide whether an anomaly represents a scientific curiosity, a potential threat, or something requiring further classified observation. 3i Atlas triggered multiple flags almost immediately after discovery. Its hyperbolic trajectory marked it as interstellar, which automatically elevates priority. Its composition anomalies detected through spectroscopy suggested material not typical of solar system comets. Another flag. Its brightness variations and outgassing patterns diverge from predictive models. More flags. Each flag doesn't mean threat, but each flag increases the object's classification level within the firewall system. By late March 2025, 3i Atlas had accumulated enough anomaly tags that it became a top-tier monitoring target for defense satellites that normally watch for ballistic missiles and orbital weapons. This isn't public information. It's pieced together from budget documents, leaked memos, and off-the-record conversations with people inside the system. But the evidence accumulates. Defense satellites repositioned to maintain line of sight on 3I Atlas as it approached perihelion. Classified ground stations increased observation time allocated to comet tracking. Interagency coordination meetings happened at classified facilities rather than open scientific conferences. The infrastructure was exercised. The protocols were activated, and suddenly a comet became a defense operation. The ethical implications are enormous and barely discussed. Science traditionally operates through open publication and peer review. Discovery data flows freely. Methodologies are transparent. Results are reproducible. But when defense networks intercept that data stream before publication, when anomalies are classified before scientists can analyze them, when observation priorities are set by military necessity rather than scientific interest, the traditional model breaks down. Who controls access to information about objects in space? Who decides what constitutes a security concern versus a research opportunity? What happens when defense priorities override scientific inquiry? Legal frameworks haven't caught up with operational reality. The Outer Space Treaty of 1967 prohibits weapons of mass destruction in space but says nothing about surveillance networks or classified observation platforms. No international agreement governs how nations share data about potentially hazardous objects. No treaty defines what information can be withheld for security purposes. We're building a militarized space monitoring infrastructure without clear rules about how it should operate or who has oversight. The firewall exists to protect us. That's the official justification. If something threatening approaches Earth, we need early warning, coordinated response, and capabilities to act decisively. No one disputes this in principle. The problem is defining threat. A natural comet with weird chemistry isn't a weapon, but it's being monitored like one. An interstellar object with anomalous behavior isn't hostile, but it's being tracked through defense channels. The system doesn't distinguish well between unknown and dangerous, so it defaults to treating everything unusual as potentially both. 3I Atlas is the test case, the first interstellar visitor to arrive during an era of operational space defense networks. The first object to trigger deep space firewall protocols and reveal how the system actually functions under real conditions. Whether it's a comet or something else, whether it's dangerous or benign, it's shown us that the boundary between science and security has already dissolved. Observation isn't neutral anymore. Discovery triggers defense responses. And somewhere in classified databases, everything we learn about 3I Atlas is being analyzed through frameworks that prioritize protection over publication. The revolution happened quietly without announcement or debate. Space militarization isn't future speculation. It's current reality built incrementally through budget allocations, classified programs, and international agreements signed behind closed doors. We're living through the normalization of defense dominance and astronomical observation, and most people don't know it's happening. 3I Atlas will leave the inner solar system eventually, but the infrastructure built to watch it isn't going anywhere. The firewall is permanent now, waiting for the next anomaly, the next unknown, the next object that makes someone nervous enough to activate protocols we're not allowed to read. Part 15. The Threshold Moment. We started with a comet and interstellar visitor rare and scientifically precious discovered in December 2024 by an automated survey telescope in South Africa. Initial reports were excited but measured. Spectroscopy showed unusual composition. Trajectory confirmed its extrasolar origin. Brightness suggested active outgassing. Standard scientific language for a non-standard object. And then slowly the story changed. Not because the comet changed, but because our response to it revealed something about who we've become. Within months, 3I Atlas transformed from an astronomical curiosity into a planetary defense event. The International Asteroid Warning Network launched a coordinated tracking campaign. Defense satellites repositioned to maintain observation. Classified platforms began collecting data through channels that don't appear in public databases. Machine learning systems flagged behavioral anomalies. High-energy particle detections raised questions about correlation. And all of this happened while officials maintained that the object posed no threat, that it's just a comet, that there's nothing unusual about any of this. That contradiction, the disconnect between official reassurance and observable response, is the real story. Because actions speak louder than press releases, and the actions being taken suggest a level of concern that nobody wants to articulate publicly. We're watching humanity's first synchronized planetary defense posture triggered not by confirmed danger, but by uncertainty about an object we can observe but not fully understand. This is the threshold moment, the point where we acknowledge that we're not alone in paying attention to visitors from beyond our solar system, and that our attention has consequences we're only beginning to grasp. What if 3I Atlas is natural? What if every anomaly has a mundane explanation? Exotic ices from a different stellar environment, outgassing patterns influenced by interstellar radiation exposure, brightness variations from irregular shape and rotation. What if scientists spending months on detailed analysis eventually conclude that it's a comet, just a weird one, unusual but not unprecedented? Then we've overinterpreted noise as signal mistaken complexity for intentionality. Let our hopes and fears project meaning onto something fundamentally ordinary. We wouldn't be the first civilization to see faces in clouds or hear messages in static. Pattern recognition is survival instinct, but it produces false positives as often as genuine discoveries. But what if it isn't natural? What if 3I Atlas carries signatures that no honest analysis can reconcile with cometary models? What if the composition anomalies persist after accounting for interstellar aging? If the brightness variations resist all attempts at natural explanation, if the trajectory adjustment suggests something other than volatile outgassing, then we face an even harder question. How would we prove it? What evidence would suffice to conclude that an object in space is artificial? And more importantly, what would we do with that conclusion if we reached it? This is the epistemological trap of technosignatures. Any sufficiently unusual natural phenomenon looks potentially artificial to limited observers. And any sufficiently advanced technology looks indistinguishable from natural processes to primitive observers. We're trapped in the middle, lacking both complete understanding of natural extremes and any framework for recognizing design systems we didn't design. 3I Atlas could be exactly what it appears to be, a visitor from another star, and we'd still argue endlessly about what that means. The precedent being set matters more than any individual object. 3I Atlas is the first interstellar visitor to arrive during an era of operational planetary defense and militarized space observation. It won't be the last. Astronomers estimate that dozens of interstellar objects pass through the inner solar system every year, most too small or dim to detect with current surveys. As telescopes improve, detection rates will increase. We'll discover more Umamas, more Borisovs, more Atlases. Each one will trigger the same cycle: discovery, characterization, anomaly, detection, defense, coordination, speculation, debate. We're establishing norms right now. Norms about who controls observation, who accesses data, who decides what information reaches the public. And those norms will govern how we handle every future visitor. What happens after perihelion 3I Atlas reaches closest approach to the Sun in late October 2025, mere days from now? By the time you're hearing this, post-perihelion observations will be crucial. Has the object survived? Has solar heating triggered new outgassing or fragmentation? Do brightness and spectroscopic signatures change as it accelerates outbound? The International Asteroid Warning Network campaign continues through January 2026, providing months of additional data. Whatever 3I Atlas is, we'll know more about it soon. Whether we'll be told what's known is a different question. And then there's the waiting for 4I, the next interstellar visitor, waiting to see if it shares characteristics with 3I Atlas, or if each object is unique, waiting to learn if hyperbolic visitors are common cosmic flotsam, or if they cluster in ways that suggest origin points, waiting for the day when an object arrives with unambiguous properties that force us to choose between denial and acceptance. That day might come next year or next century, but the infrastructure we're building now determines how we'll respond when it arrives. Here's what we know with certainty: the universe is vast beyond comprehension. Our galaxy contains hundreds of billions of stars, probably trillions of planets, and more raw material than we can meaningfully quantify. Statistical reasoning suggests that we're not the only technical civilization to have emerged. The laws of physics allow for interstellar travel, even if the engineering challenges are immense. And now, objects from beyond our solar system are arriving where we can observe them carrying information about places we've never seen. The universe knocked on our door. Whether we opened it or slammed it shut, whether we chose curiosity or paranoia, transparency or secrecy wonder, or fear we may never know who was behind it. But we answered one way or another. We mobilized telescopes and satellites, activated defense networks and classified protocols, deployed artificial intelligence and human expertise. We treated an interstellar comet like a potential threat because we've become a species that thinks in terms of defense before understanding. That says something about where we are as a civilization, about what we've learned from history, and what we've lost along the way. 3i Atlas is still out there approaching the sun, shedding volatiles, reflecting light that left its surface hours ago. It doesn't care what we think about it. It doesn't notice our telescopes or our anxieties. It follows the equations of orbital mechanics with perfect indifference. A messenger from the galaxy that might be delivering a message we're too frightened to read. Stay alert. Keep watching. Question the official narrative, but also question your own assumptions. The storm may not be over. It might just be beginning, and the next object to arrive on a hyperbolic trajectory might not give us the luxury of years to debate what it means. We're at the threshold, standing between the solar system that raised us and the galaxy that surrounds us. What happens next depends on whether we choose to step forward or pull back, whether we embrace the unknown or fortify against it, whether we're ready to be part of something larger than ourselves or determined to remain isolated behind walls we built from fear. The sky is full of visitors. We're only just learning to see.